Good morning, everyone. How are y'all doing today? Doing good. My name is Christopher Neeley, and I'm here to present a professional presentation on supercomputing. So to start things off, what is a supercomputer? Does anyone know?
Big computer.
Big computer, that's a good guess. Oxford defines a supercomputer as a particularly powerful mainframe computer. And the performance of a supercomputer is measured in what is known as floating point operations per second, or FLOPS for short. I'm going to get into a history of supercomputers now. Introduced in 1929, the first supercomputer was a tabulator that was built by IBM for Columbia University. It used punch cards as its input and output methods for data storage. Flash forward to 1960, the beginning of the modern computer era. Control Data Corporation, in partnership with Seymour Cray, created a supercomputer called the CDC 6600. This supercomputer was revolutionary for its time and was widely considered to be the first entry into the modern supercomputing age. It ran at about 1 megaflop, which was astronomical at the time. Another groundbreaking supercomputer, which was developed in 1962 in England, was known as the Atlas. The Atlas pioneered the use of virtual memory and paging as a way to extend Atlas's working memory by combining its 16,384 words of primary core memory with an additional 96K words of secondary drum memory. Drum memory was an early method of magnetic data storage. Atlas also pioneered the Atlas Supervisor, which was widely considered to be the first operating system. Moving into the 1970s, another entry from Control Data Corporation, the Star 100, which was introduced in 1974. It was the first to use a vector processor to improve performance on appropriate scientific applications. A vector processor, or also known as an array processor, is a central processing unit that implements an instruction set containing instructions that operate on one-dimensional arrays of data called vectors. So for its time, the Star 100 was making good headway towards supercomputing as we know it today. It was also the first to use integrated circuits. Getting into the 1980s now of supercomputing, in 1985, Seymour Cray re-entered the cutting-edge supercomputing world with his latest entry, the Cray 2. The Cray 2 was a 4-processor, liquid-cooled, totally immersed in a tank of floor inert, which bubbled as it operated. It could perform a whopping 1.9 gigaflops, and that's in the 80s. The Cray 2's design was improved upon with the introduction of the Cray YMP, which used 8 vector processors and ran at about 333 megaflops per processor. That's a whopping 2,664 megaflops. The Cray YMP held the top spot for supercomputing until the early 1990s. In the 1990s, supercomputers with thousands of processors began to appear, leading the way in the early to mid-90s were Japanese companies like Fujitsu and Hitachi. Fujitsu's numerical wind supercomputer used 166 vector processors, and it had a peak speed of 1.7 gigaflops per processor. That's a lot of gigaflops. Following that up, Hitachi introduced the SR2001, and it obtained a peak speed of 600 gigaflops in 1996 using 2,048 processors connected via a fast 3-dimensional crossbar switch network. Then suddenly in the 1990s, a huge company came about, Intel. In the same time frame, the Intel Paragon could have 1,000 to 4,000 Intel i860 processors in various configurations. The Paragon was what is known as an MIMD machine, multiple instruction, multiple data, and it is a technique employed to achieve parallelism among all its processors, which were connected via a high-speed two-dimensional mesh, allowing processes to execute on separate nodes, communicating it via its passive messaging interface. Each processor of the Paragon was capable of 75 flops. Moving into more modern-day computers, capitalizing on Paragon's architecture, Intel developed their next supercomputer known as ASCII Red in 1996. ASCII Red was also a mesh-based MIMD massively parallel system with over 9,000 computer nodes, as well as 12 terabytes of disk storage. But amazingly, it used off-the-shelf Pentium Pro processors that could be found in everyday personal computers. ASCII Red was the first supercomputer system to ever break the 1 teraflop barrier. Moving into our modern-day supercomputing, significant supercomputer advances were made in the first decade of the 21st century, and the efficiency of supercomputers continued to increase. A revolutionary computer built in 2004 is known as IBM's Blue Gene supercomputer, and this was a dramatic leap forward in supercomputing power, as well as the energy it took to provide that power. The approach Blue Gene took was somewhat different in that it trades processor speed for lower power consumption so that a larger number of processors can be used at air-cooled temperatures. It used over 60,000 processors with an additional 2,048 processors per rack, and connected them also via a three-dimensional torus interconnect. Torus interconnect, by the way, is a switchless networking topology for connecting processing nodes in a parallel fashion. The Blue Gene ran at a peak of an astounding 596 teraflops. Blue Gene's main goal was to simulate the human genome through a process known as folding, which is a study in biology on folding proteins and the genetic study. Capitalizing on their groundbreaking success with Blue Gene, IBM followed Blue Gene up with the Roadrunner. The Roadrunner was built by IBM, designed for a peak performance of 1.7 petaflops. It achieved 1.026 petaflops on May 25, 2008, to become the world's first supercomputer to sustain 1 petaflop. The Roadrunner was the first supercomputer to sustain 1 petaflop using 12,960 IBM Power XL and 6,480 AMD dual-core processors. That's a lot of processors. It was used by the Department of Energy and the National Nuclear Security Administration for nuclear research and nuclear testing. Let's fast forward to the year 2018. In just 10 years after the IBM Roadrunner was commissioned, IBM came in with another supercomputer that we all may know, Summit, housed at Oak Ridge National Laboratories. Summit is a supercomputer developed by IBM for Oak Ridge National Laboratories, which as of 2018 was the fastest supercomputer in the world, capable of 200 petaflops. After some tweaking and some more instruction sets were added to it, Summit eventually reached a peak of 1.8 exaflops, becoming the first supercomputer in the world to pass the exaflop barrier. Plans are currently in the works to develop a new supercomputer here in Tennessee known as Frontier. The supercomputer designated Frontier is currently being developed in conjunction with Cray Research and Oak Ridge National Labs. Expected to reach a peak speed initially of 1.5 exaflops. Further programming and further data management should allow the computer to reach speeds as high as 5 exaflops. Oak Ridge National Laboratory's goal is to become the #1 supercomputer in the world. Frontier is expected to be finished by 2021. So what are supercomputers used for? Anybody have any ideas, like what they could be used for?
Google.
Google? That's a good answer. Sir?
Very, very, very heavy calculations.
That's right. Heavy calculations. And what is heavy calculations good for? Medical industry, biology, military uses, engineering, physics, astronomy, robotics, and much more. I have a quick video for you all.
You know what's better when it's more floppy? Supercomputers. Hey everyone, Julian here for D-News. China has just announced that it's creating
Even
the
though we
most
don't
powerful
know China.
supercomputer yet. The machine, named Sunway High Light, is theoretically capable of almost 125 petaflops, or 125 million billion flops. I don't mean 125 million billion football players, I mean flops, a metric of computer speed. It's an acronym which stands for floating point operations per second. It basically translates to how many calculations they can do with gigantic or infinitesimally small numbers in 1 second. Because supercomputers can do 100 million billion calculations every second, and because the range of numbers it's able to use is so incredibly large, supercomputers are perfect for running models that deal with things of all sizes, from how galaxies form to how atoms interact. In other words, they're ideal for science. Every time we mention on D-News that an experiment used a computer model, they did it on a supercomputer. These computers can be privately owned, as is the case with some pharmaceutical companies that use them to model how a drug will behave on a molecular level. Supercomputers can be ludicrously expensive though. Sunway Time Light cost $270 million to research, develop, and build. And that's before the cost of operation are factored in. Imagine how much electricity it takes to run a supercomputer as big as your house, and how much it would cost to keep it cool so said house didn't melt itself. For that reason, more often they're paid for by a government, and then that government decides what experiments are awarded access. Sometimes supercomputers are built with just one purpose in mind, like IBM's Deep Blue, which was made to beat one guy at chess in 1997. 2 years later, they made Blue Gene with the purpose of studying how proteins folded and to make a really lame pun. Usually those supercomputers can be general purpose. They've been used to test nuclear weapons, not just the explosion themselves, but everything that could affect how they work, from when they're pulled out of storage to when they go off. Even little things like how much a transport truck rattles could have an effect on a nuclear missile's guidance system, so it's factored into the calculations. And all this can be done without actually setting off a nuke, so they're making our deadly weapons safer, I guess. Supercomputers are invaluable to astronomy and cosmology, modeling the first few moments after the Big Bang on an atomic level, or what happens during a supernova. They've been instrumental in simulating how a protein can fold itself, because they can track how every single atom will interact with those around it. This can also be used to figure out why proteins sometimes go wrong and cause diseases. And for our day-to-day lives, they have been most noticeably useful for predicting the weather, taking in information from hundreds of thousands of weather stations around the world and comparing it to the data from yesterday to predict what will happen tomorrow. Extending that much farther and using averages instead of specifics, supercomputers can be used to simulate climate change. They're the only beasts powerful enough to take in the many, many variables that go into predicting the climate far into the future. And there's still room for improvement. When they crack the next milestone in speed, the exaflop, or a billion flops, scientists think they'll be able to make a fully coupled Earth system model that is accurate down to a kilometer. Every variable a scientist would want to include for the entire Earth down to a kilometer resolution, all calculated before I die of old age. That's what I call a supercomputer. If there's one thing you don't need a supercomputer for, it's creating your own website, and you can stake your claim to a quarter of the internet thanks to domain.com. No domain extension will help you tell your story like a .com or .net domain name. And because you watch D-News, you can get 15% off domain.com's
In conclusion, supercomputing has come a very long way in a very short time. Practical uses of powerful supercomputing will continue to develop and evolve as time goes on. And that's all I've got for everyone. I thank you all for attending, and I hope you have a wonderful day.